Hi, my name is Jim, and today's topic is frequency modulation, and that's one of the forms of angle modulation, and angle modulation also includes phase modulation, which is used a lot in digital transmission, but we're going to limit our discussion here today to just frequency modulation. Now, historically, the way this came about is that in the days of old, and even in the days of contemporary transistor radios, it's very critical that the local oscillator be exactly where it should be, which is in high side injection, the intermediate frequency above the station that's tuned. Now, especially in the days of old, where you're dealing with vacuum tubes which have filaments which get quite warm, plus the electronics gets quite warm also, is the local oscillator had a tendency to drift. Now that comes about because the various parts expand a little bit when they get warm, and in so doing, when a radio warms up, what you'd have to do is go over and retune it. The same is true for televisions. So a fix for that was kicked about, and what it kind of looks like is an AM radio with an additional stage here, which is called a discriminator. So just the way it works is we have an antenna, a nonlinear mixer as before, a local oscillator which heterodynes against the incoming radio frequencies, and the cross product terms for the desired station will produce an intermediate frequency. In the case of AM, that would be, say, 455 kilohertz, which is amplified, detected, and goes out to our volume control and then to our audio stages. I did not show the antenna tuning in here. So what the discriminator does is it taps off the output of the IF, and what it produces is a correction voltage based upon the input frequency. So if everything is correct and the input frequency is, say, 455 kilohertz, the output is kind of a DC voltage, would be 0 volts feeding back into the local oscillator. If the local oscillator drifts, the IF is going to change. The discriminator is going to output what's called an error voltage and tend to bring the local oscillator closer to back where it should be. So this is the same as cruise control, which I used an example before, is a form of negative feedback. Will it bring the local oscillator back exactly on frequency? No, it can't, because if it did, there would be no error voltage for it to work with. But it works well enough so that you don't have to get up and retune it. Now, transistor radios also have AFC options. Right behind the camera there's a Zenith radio that has AM, FM, and FM parentheses AFC. So to tune in an FM station, you'd put it on FM without AFC, get it exactly tuned in correctly, and then flip the switch to AFC, and it'll help lock it in. On some transistor sets, when you touch the tuning knob, it turns off the AFC. You make your adjustments, you release the tuning knob, and it turns the automatic frequency control, I guess I should have told you that, back on. So that's AFC. There we go. Automatic frequency control. Now, what was noted, and again the founder of this, the inventor, was Major Armstrong, is that if we replace the antenna, say, with a signal generator, it's tuned to the desired station, and we connect the scope to this point. If we take our incoming station, say it's, I don't know, 1300 kilohertz on the AM dial, and wiggle that back and forth, as we'll see the correction voltage also wiggle in accord with it, trying to correct the IF, because the IF is a function of the incoming frequency and the local oscillator. Now, the incoming frequency by FCC standards for a standard AM broadcast station is allowed plus or minus 10 hertz to be in specification, so that's pretty tight. Anyway, wiggling this here would produce a correction voltage, and what was noted as if you change the incoming frequency, say in a sinusoidal manner, the correction voltage would also exhibit a sinusoidal behavior. So in an FM radio, all we have to do would be break this and connect this point to our audio, and then if our input is frequency modulated, the output of the discriminator will actually produce a modulating voltage, which is causing the frequency to change. So FM grew out of a problem with AM, and obviously it's quite widespread today. It's only recently been challenged by satellite radio and things like that. So let's take a better look at this drift problem with. Here what we're looking at is a radio from the 1930s. It's an AM broadcast receiver. It's per se a table model radio. It either lived inside of a wooden cathedral cabinet or what's called a tombstone. It'd be about this high. It's made by Philco. It's a high quality radio. It's AM plus shortwave. And what I'm going to do is, it's tuned to a station now, and it's about 11:30 on a very cold night, so there's a lot of skip. That is signals coming in via the ionosphere. And what I'm going to do is put my finger on the local oscillator capacitor, changing the capacity a little bit with my body, and tune in a different station, and that should make it very clear as to what this drift is all about. This is the second station, and that is the primary station. So you see the drift can be very annoying, having to get up and retune things, and it's because of that, trying to solve that problem, is the forebear for frequency modulated radio receivers. So taking a look at some relatively crude fundamentals here, if we have a carrier wave, and before we apply modulation, this is going to be the assigned frequency, say 90.1 megahertz. In any commercial FM band, channel spacing is 200 kilohertz. So it'll be like 90.1, and the next station on the high side would be 90.3 and 90.5, and so forth. And what we see with our modulating voltage here is this goes positive, is that the frequency of the carrier wave increases. And we can tell that because the period decreases. Likewise, when the modulating signal goes negative, the frequency decreases, as you can see by the increased period. And therefore, we have the modulating voltage controlling the frequency of the carrier. Now, at any point in here, the instantaneous frequency varies from the maximum, and that's called deviation. Positive deviation, that's where the carrier deviates upward relative to the peak, or I guess I should say as determined by the peak, and then the maximum downward deviation, where the frequency becomes lower, which is determined by the negative peak of the modulating waveform. Now this could be reversed. It could be that positive going produces a lower frequency and negative going produces a higher frequency. Doesn't really matter. So that's kind of what it looks like, the carrier and the modulating frequency. And what's very important to note here is that the amplitude of this does not change with modulation. It's essentially constant. There's something called incidental AM, which results in the modulating process, but the receiver strips it anyway in a circuit called a limiter, and we'll talk about that in the future. So if the voltage remains the same, the power remains the same, what carries the information? And the answer to that question is that power is taken away from the carrier and placed in the sidebands. And the sum of all the sidebands plus the carrier is constant. And that constant would be the same as an unmodulated carrier. So, let's see here. Carrier frequency changes in accord with the modulating voltage, and that's called deviation. The carrier voltage and power do not change with modulation, very important. And the amount of deviation controlled by the amplitude of the modulating voltage. So, if the amplitude of the modulating voltage became higher, then the deviation would increase, meaning that the frequency of this part would be higher than it is here. So if I had a modulating voltage, say, that looked like this, the deviation frequency here would be higher than it is at that point. So we got to measure things. That's the way it is. And again, m is the coefficient of modulation, and it is defined as the deviation delta f divided by the modulating frequency. And like in AM, we're going to be using sine waves in this. Complex waveforms would be very hard to analyze. And if we just take a look at a channel here, an FM channel, the FCC assigns the carrier frequency, say, I don't know, use a different number, 93.5, and the carrier is permitted to deviate plus 75 kilohertz and minus 75 kilohertz in accord with the modulating voltage. And then on each side of this we have a 25 kilohertz guard band. The total channel spacing is 200K, and then 200 kilohertz away would be the next assigned carrier channel, if you will, radio station. And sitting in here would be another 25 kilohertz guard band. So the FCC usually does not assign adjacent channels, and the same is true with AM and with television for that matter, in the same city. But like I was picking up skip before, that can happen in FM to a little bit lesser of a degree because of the higher frequencies. So that's the channel bandwidth here, sits in at 200 kilohertz. And ideally it should occupy 150 kilohertz with regard to the deviation of the carrier. Now we have a modulator which makes the carrier wave and deviates it in accord with the modulating voltage, and it has a sensitivity factor called K, and K is the frequency deviation divided by the voltage which causes that deviation, and it's a constant. And suppose, for example, that K equal 10 kilohertz per volt, and the modulating voltage is 0.75 volts peak. What we would have for deviation then would be the modulating voltage times K, 0.75 voltage times our constant here, and that would give us 7.5 kilohertz of deviation. Now what to note here is that the units of volt divides out, and what we're left with is a frequency which we would expect if we're talking about frequency deviation. Okay, we're going to get into some details here in a minute, but again, total power does not change with modulation, and the carrier voltage and power shift into the sidebands, and the number of sidebands is a function of m, the modulating coefficient. Now with a sine wave, unlike AM, we can have more than one sideband pair. So down here I've kind of illustrated that, and this is going to be in the frequency domain. Let's put a little F there, and I'll put a little F there. There we go. So an unmodulated carrier would look like a single spectral spike, and always remember that spectral spikes are sinusoids. There's no triangle waves or square waves in a spectral spike. It's a sine wave. And then if we apply modulation, what we see is that the carrier dropped. The first sideband pair in black popped up, second sideband pair in red appear, and the third sideband pair in blue also appears. So we can have many sideband pairs, or in narrowband FM, used in, say, taxicab communication, it's limited to the first sideband pair, and the bandwidth competes favorably with AM. So we've got a different situation here in AM, is that as we apply a modulating voltage, as we see these sideband pairs appear, and then if I were to increase the modulating voltage, the first sideband pair may shrink, the carrier may grow, the second may grow, in accord with what's called the Bessel functions. Now, Bessel functions are relatively complicated mathematically, but they're broken down in tables for us that should make sense. So we're going to take a look at those next. So this is the function in tableized form, and you have this graph in one of your folders. And what we have here is M, the coefficient of modulation, and J0 stands for the carrier voltage. J1 is the first sideband pair voltage, J2 the second sideband pair voltage, and so forth. And what you see is that M increases. What we get is more and more and more sidebands, and then some of these are kind of insignificant, like that 0.01 and so forth. So let's just take a look at a carrier without any modulation, and that would be M equals 0. So what we see is that 1.00, and this is normalized. So this is, say, referencing itself to 1 volt, appears in the carrier. Now, if we say increase the modulation, suppose we apply a modulating signal of 1 kilohertz, and M, the modulating index, is 1.0, so what that means is that the deviation would be 1 kilohertz and the modulating frequency is 1 kilohertz. Is what we see is that the carrier voltage drops to 77%, a first sideband pair is 44%, second sideband pair is 11%, and a third sideband pair is 0.02%, and then the rest are considered to be insignificant. Also note on here, if we're sitting at a mod index of 2.4, say a 1 kilohertz modulating signal producing a deviation of 2.4 kilohertz, the carrier is 0 volts. It's gone. First sideband is 52%, 43%, 20%, 6%, 2%, and so forth. So this is called a carrier null. And on this graph, there's only one of them showing, which is at M equals 2.4. But here we go from negative to positive, so there's another null in there someplace. So it's kind of interesting that the entire carrier can go away. But what you should be gleaning from this is that the sidebands can really spread out a lot. And the sidebands are going to be, as in the case of AM, a multiple of the modulating voltage. So let's take another look at this, only this time it'll be from the standpoint of an analog graph. And although this is a little bit more difficult to interpret, it tells us some things. That looks good. So in this, our mod index is across the bottom here, and we're going to start with our J0 being this line, and note that when M equals 0, 100% of the voltage is in the carrier and 0% is in any of the sideband pairs. So if we increase the mod index, say to 2.0, there we go, get this ruler here, and we carefully hold this up like so, as we can see that the first sideband pair will be approximately 0.6, 60%, second sideband pair I'm estimating at 40%, third sideband pair in light blue here, maybe 20%, and the carrier now is sitting way down here, just about the same as the third sideband pair. Now, when the carrier J0 goes negative, all that means is that the phase of the carrier shifted 180 degrees. Keep in mind that P equals V squared over R, so we still have a positive power when this happens. And as you can also see here, as M increases, we have more and more significance in the sideband pairs. So there's advantages to using an analog table here. I think it portrays things a little better, but it's a little bit harder to read and figure out what the actual relative voltage is, because you're interpreting a graph. And if you go to use this, it's always a good idea to put a straight edge here. So say you're at 3.5 at the bottom, you're also at 3.5 at the top. So you can get a better idea of what the sideband pair voltages look like. Now while I've got this up, let's take a look at this. And we've seen this before. Put them up here, there we go. And let me just check the, yeah, he looks good. In this we discussed an AM, and what we had is relative to the carrier phasor, this guy right here, we had the upper and lower sidebands as represented by phasers, which were drawn relative to the carrier phaser, and the upper sideband phaser is rotating counterclockwise and the lower sideband phaser is rotating clockwise. If you recall, we added these together, and when we did that, we generated the envelope, which isn't really there. It's just a shape of the actual carrier frequency as amplitude modulated. So these phasers drew a pretty good diagram of what was going on. Now let's do the same thing in FM. That might give us some insight on what's going on. And ironically, this looks a little bit different. Let me check that. Yeah, it looks good. The only thing that's different basically is that the carrier and sidebands are 90 degrees out of phase. So here we have the lower sideband and the upper sideband adding together, and this little guy here, M, represents the phase shift from the carrier unmodulated to the carrier when the sidebands are adding together. And likewise, again, the upper sideband is rotating clockwise, lower sideband counterclockwise. As we see now, this angle is going to decrease, and when the sidebands are opposing, carrier frequency is going to be, or carrier phase more correctly, is going to be exactly where it should be. And then as the sidebands phasers again start to add up, it'll push the phase of the carrier down and then come back to zero. So the phase of the carrier is being shifted, and what we need to remember is that frequency is the rate of the phase change per unit of time. Okay, it's d phase dt. So we're seeing the phase change, and that's also producing a frequency shift. Now if we looked at this from the standpoint of the whole thing here, is what we would see would be the carrier would produce something that looks like this. So that's the locus of the first sideband pair, and what this leads to is a little bit of amplitude modulation that's sneaking in there. It doesn't carry any information, it's just an artifact of the modulation process, and that amplitude modulation is stripped in the receiver, and it's stripped along with things like static interference and so forth. So an FM receiver is not sensitive to variations in amplitude of what is coming in. Okay, we have all kind of sidebands popping up depending upon M. So what is the bandwidth actually going to be of an FM signal? And there's two ways to do this for high quality. It's commercial grade FM, and that would be 2 times the maximum deviation. So in the case of our 88 megahertz to 108 megahertz FM band, this would be 2 times 75 kilohertz, which equals 150 kilohertz. And then there's also Carson's rule, which the bandwidth is equal to 2 times the deviation plus the modulating frequency. So if the deviation is, say, 75 kilohertz and the modulating frequency, worst case, is 15K, we end up with 90 kilohertz times 2, which is 180 kilohertz. Now, what the actual bandwidth is it can go out to infinity. But as the outermost sidebands become lower in amplitude, they contribute less and less to the overall quality of the signal, especially the signal-to-noise ratio. So when we say bandwidth, these are practical bandwidths. Then in narrowband FM, like for taxi communications, and used to be fire and police at one time also, the bandwidth would be equal to 2 times FN, and for speech, the frequency in was limited to about 3.5 kilohertz. So the bandwidth of this was similar to that of AM. Which is nice because you get the benefits of FM, meaning somewhat noise-free, with the same bandwidth as AM. And this has a lower signal-to-noise ratio than the higher quality systems where the bandwidth can vary quite a bit. It's quite a bit larger. So let's take a look and see if FM is truly noise immune. When I first discovered FM, I was recording rock music on a tape recorder in a thunderstorm, and I simply couldn't believe it. I didn't hear any cracks of lightning or anything else in the music. So here we've got an FM signal here, and in blue there's a noise pulse. And what I've done is I've put red dots where the carrier crosses the zero line. And then over here what I've done is I've superimposed the noise on top of the carrier signal. And what we see over here is when the noise occurs is that the amplitude of the carrier, and this would be in the receiver, increases. It's additive, we'll say. But it doesn't matter because the receiver has a stage called a limiter, which is basically going to whack the tops and bottoms from the intermediate frequency of the FM radio, and in so doing will eliminate any changes in amplitude. However, do note that the crossover point here is shifted. Now, this basically means that the phase is shifted, and what we know is that frequency is a function of phase change. So we cannot say that an FM radio, an FM transmission system, is completely immune to noise caused by man-made sources or atmospherics or anything like that. There is a bit of phase modulation which occurs, which will decrease the signal-to-noise ratio. Now, FM came about in the 1950s for real, and FM radios were fairly expensive then, and a lot of work was done in England. And one of the annoying problems with FM is it had this hiss characteristic that was present in the audio, and I'm going to reintroduce the term baseband signal again. So, in order to fix that problem, there's a little bit of distortion that was added at the transmitter, and that distortion is called preemphasis. And it was found that a frequency, 2.12 kilohertz, was a good corner frequency. And what happens after that is any frequency components in the speech or music gets emphasized, that means increased, at a rate of plus 10 dB per decade. So if we were to listen to this out of the preemphasis network, the higher frequency components, like the sound of a cymbal on a drum, would be too loud relative to what they should be. Now, to make up for this pre-distortion is that every FM radio made has a de-emphasis network. That's this guy. It has the same turnover frequency, only its response is negative 10 dB per decade. So as this will reduce the hiss, it'll also take our emphasis and put it exactly where it should be. So if we were to look at this from the standpoint of our overall, that's transmitter to receiver, frequency response, we'd find that these offsetting airs produce a flat response, but yet the response from noise, hiss, would look like this. And this would be a negative 10 dB per decade roll-off. So this idea of pre-distorting and then fixing it later is very, very effective. Now you might be thinking, well, what if I put on a 15 kilohertz signal that would, if we didn't have this, produce the same deviation as that of 1 kilohertz, which would be 75 kilohertz. Now that we've emphasized it, it would be way out of range, and that would be correct. The issue is, in typical program music, is that the higher frequencies occupy much, much lower of a voltage than the lower frequencies. So we actually don't have that problem. So how do we produce preemphasis? And I've kind of drawn two circuits here. Well, one is a bipolar circuit, and in that circuit we have, this would be the supply voltage, an inductor in series with a resistor, and what we know about the inductor is that its impedance is controlled by the frequency. It's a function of the frequency. It's 2 pi FL. So as the frequency increases above the corner frequency here, which is 2.12 kilohertz, so does the load of the transistor, and that means the gain goes up. So the gain will increase, and the time constant of this T, tau, would be the L over R would be 75 microseconds, which is the standard for the commercial band. Or you could look at it as a high-pass filter. C in series with an R, and the time constant tau equals RC also equals 75 microseconds. Now in the receiver, this is the simplest de-emphasis network in R and the C, and as probably guessed, tau is equal to 75 microseconds. That basically means you have a wide range of, well, theoretically an infinite range of R and C that you can use that'll give you the time constant, and no matter what your values are, as long as the time constant is the same, is you'll get this correcting factor. Now the same thing is done when you speak out of your local exchange. On your regular telephone line, your voice is compressed, and that makes an 8-bit system look like 10.5 bits. And when it gets over to the receiving central office, it's called, of the person you're talking to, it's uncompressed to make it the same as it was almost when it started out. So that's another case of pre-distortion and then fixing it later. And they can't do that in a lot of different situations, but if it's controlled and built into the system, it is manageable. So that was one of the big improvements here to produce the quality of FM radio. Now we're not going to discuss stereo in detail when we talk about receivers, but in the early days of stereo in the 50s, they used to broadcast, and people were directed to take an AM receiver and say put it on the left side and an FM receiver on the right side, and then the broadcasters would feed the AM station, say, with the left channel, and the FM station with the right channel, and people could experience stereo, sort of. AM is limited in bandwidth, as you know, to 5 kilohertz. Further, the stereo image is very dependent upon the left and right signals arriving at the right time, and that probably didn't happen very well. So there was a tremendous effort made to introduce stereo in the FM, and that came about in the late 50s, early 60s. The FCC mandate was that it had to be compatible with monophonic FM. Now, going back in history a little bit, again to Major Armstrong, the first FM channels were located in 41 to 43 megahertz band, and that was in the Second World War and post-war, and the FCC elected to use that frequency for highway mobile radio use and relocated it up to 88 to 108. So people that bought radios, AM/FM radios, couldn't use FM anymore, and those radios were very expensive. Hence, when it came to producing FM stereo, it had to be compatible with FM monophonic. Now, how do you make FM? Well, we have an oscillator here, and in it we'll take a look at a tuned circuit, and we're going to connect across that something called a condenser microphone. Now, in days of old, capacitors were called condensers, but in modern language, condenser's been completely replaced by the term capacitor, except in condenser mics. Now, the way it works is that there's two diaphragms, and when speech strikes one, it vibrates in accord with the air pressure waves and changes the capacity. So what you can see here is this plate moves back and forth. It's going to increase and decrease in capacity, which is going to vary the resonant frequency of the tuned circuit and then produce a frequency modulated output. Now, there's a lot of other and better ways of producing FM, but this is the simplest and the easiest to understand. So that should do it for FM creation and FM transmission, and then we'll visit FM receivers next topic. Thank you for watching.